Actually, I was thinking, I mean, do you actually have a plan for today?
Yeah. I made some stuff like just beforehand, like yeah. So we're going to go over eigenvectors today, and if time, you'll try and go over convergence and divergence, and if you want, I can try and touch on integrals. I'll see. Probably try and make a video about that. I should say I feel like shit today, so do ignore, do mind the swearing or whatever. So there isn't too much with eigenvectors. I guess the main thing is just trying to go over loads of problems, but I will go over like the proofs and what was the other stuff? Oh yeah, a couple of other cool applications of eigenvectors. Yeah, I guess I should start, shouldn't I? I knew you were going to record it after 20 minutes or whatever, right? Sweet. Okay, so we're going to start off with the definition of the shit. Ax is equal to lambda x. Okay, so we're going to start off with the definition of an eigenvector. So let's say you have some matrix A that looks, say, something like this, A, B, C, D. And you're going to times it by some vector x. I'm going to say xy. And what you're going to get out with eigenvectors is simply the same vector, but times by some random constant, and we're going to call that constant lambda. And usually they call these eigenvalues and eigenvectors. And so the idea is, you apply your matrix to your vector, and then out comes out the same vector, just with a slightly with a weird number at the beginning. And so that's cool. That's our definition. But then we need to try and figure out actually like how to find our x and our lambda. And so I'm going to go over the real quick proof of it. So if we start off with that, move that to the other side. And I'm going to times everything by I. Are you all familiar with I, the identity matrix? Yeah. So something on the lines of I, for a 2x2 case, it's something like that. So we're going to times, well, AI obviously is just going to be still equal to A. But our lambda I, and we get some x equal to 0. So we can rub out this I here, make it look a little nicer. And we're going to factor out some x A minus lambda I. And you can sorry? Say what? Oh, right, okay. Well, that destroys the proof, doesn't it? Let's just stick with it for now. And so you want to be on the other side? Oh, on the other side. Okay.
2 by 2 multiplied by 2 by 1.
So like that?
Yeah.
Okay. Oh, right. Okay. Oh, right. Okay. Sorry. I thought you meant like you couldn't do that. I was like, oh shit. Okay. So normally, like in like linear algebra and stuff, if you had something like A times by B equal to 0, you could just say that your you could just say that A is equal to 0 and B, well, either A is equal to 0 or B is equal to 0. But we can't quite do that with matrices. With matrices, because like this times by this means something weird. This is just a representation of something like that. And so in matrices, you actually don't have a divide function. You have a times, you can add, but you can't divide. And so we can't actually, I'd love to just say x is equal to 0 and this is equal to 0, but we can't really do that. And so what I'm going to do here, rub that out, is I'm going to introduce a new variable b. I'm going to say this bit here is equal to b, so we get some b times by x is equal to 0. Now here I'm going to assume a couple of things. I'm going to assume that x does not equal to 0. Yeah. And I'm going to assume that b times by b to the minus 1 is equal to I, which is the same as saying the determinant of b is not equal to 0. So x not equal to 0, as my boy Sam just put it, that's a trivial solution. We ain't worried about the trivial solution here. We're worried about the good solutions, isn't it? So we're going to say we don't want x is equal to 0. Because if you put 0 here, no matter what your matrix A is, what A is, if this is 0, this is going to be 0. And so the second assumption we're going to make is that the b times by b to the minus 1 is equal to the identity. So B times its inverse is equal to identity, which means the same thing as the determinant of B is not equal to 0. And so now I'm going to times both sides here by b to the minus 1. Bx, b to the minus 1, 0, times by some 0. So this obviously is going to be equal to 0. And this thing here is equal to identity. So we get x is equal to 0, which is not good. Because that goes against one of our original assumptions. It says we don't want x equal to 0. We want all the other cases. And so something must be wrong with our initial assumption. So proof by contradiction, we're going to say that the determinant of b is actually equal to 0. Det b equals to 0. And so b is this part here. So what you might see written out quite a lot is they tend to write something on the lines of a minus lambda I is equal to 0. And so from this, we can try and, it's a lot easier to work out our eigenvectors. If I give a general form of it, a minus lambda I. So a is a, b, c, d.
Sorry, can you just let the marker?
All right, sure. Shit. Shit. Oh, okay. And so we have a, so can you see this bit? These words, shall we write them? You can't see those, okay. So, yeah. A minus lambda I, determinant is equal to 0. So these two lines just mean work out the determinant of whatever's inside. So if we give the general case A, B, C, D, that's our A, minus our lambda times by identity, 1, 0, 0, 1. And so we just get the determinant of A minus lambda, B, C, D minus lambda. Oop. Yeah. So that's generally, so from this you can kind of work out what your eigenvalues are going to be. What did I say? This is equal to 0. And so yeah, that's the way we're going to work it out. So we go through an example. First, anyone have any questions? Some just say the proof's very confusing at times. Yeah.
Why is it just B?
Why is it just B? Say again? You're saying about this B? Oh, because you're minusing it from the identity. If you like, this lambda times by here will give you lambda, and this times here, if I write it actually, A, B, C, D. So you get where this came from. This came from the A. And if I expand this out, you get lambda, 0, 0, lambda. And then you subtract each term, and then you get that.
Oh, yeah, okay.
Cool. Okay. So if I take, yeah.
May I just add that, matrices normally need transformation of vectors. Now, vectors are normal objects, and matrices are just some sort of transformation. Sometimes they make sense, sometimes they don't. But when they do make sense, you probably come across rotation matrices or translation matrices, stuff like that. And eigenvectors are those objects or vectors which don't change even on being transformed. So for example, rotation along x-axis, that would rotate all sorts of vectors in y and z directions, but it will always keep all the vectors in x directions the same. So any vector along x direction would be an eigenvector to the matrix which rotates along x direction. Yeah.
Cool. Oh boy. Okay, so was it 8, 3, 2, 7? So given that, we're going to work out its eigenvectors. So using that thing we made over there, we say that what we're trying to work out is the determinant of this equal to 0, and so from this you get 8, 9. So with a 2 by 2 matrix, the determinant is that number times that number minus that number times that number. That's just a definition. I don't really know where it comes from, but yeah. Minus 6, and then from this you get a quadratic equation that looks something like x squared minus, is it 15? 15. 15 lambda 50 equals 0. And you get lambda equal to 5 and 10. I did that all in my head. I did not write it here. Okay, now we're going to use this little thing out over here to work out. So now we've got our eigenvalues, 2 values. And we're going to, from these eigenvalues, we're going to work out our eigenvectors using this thingamabobbin. So if we write it out, 8, 3, 2, 7, and we don't really know what our vectors are, so we're just going to give them like placeholder values, x, y, equal to some lambda times by x, y. So from this we get matrix multiplication. We can get 2 simultaneous equations. So we get 8x plus 3, actually not really simultaneous, but whatever, equal to, I'm going to use the first lambda we have here, 5x, and you get from this 3y is equal to minus 3x, or simply put, y equal to minus x. And so now we know that so you could do it for both cases. I'll do the other one as well. 2x plus 7y equal to 5y. And that gives you the same y equal to minus x. So now we know a kind of line that our eigenvector lies on. So like this is some line, and our eigenvector has to lie on this line. And so we can say that our eigenvector 1 has to lie on this line. So if I just put some random x value, I choose an x value, and then I put it into the equation, our y will then equal to minus 1. If you like, that's our first eigenvector. And like, if you wanted to, you could always just do this, which normalizes it and means that it has a magnitude of 1, and it tends to help, like, because it means it won't mess up with the magnitude of, like, say, the rest of your equations. And then the same way, you do the same thing for the second one. I'm sure you've seen this before. And the second vector is 3, 2. One thing to note is that we're not, our eigenvector can kind of have any magnitude. So what I mean by this is an eigenvector, but equally, 5 minus 5, this is an eigenvector. And 5, 0, 0, 0, 0, 0, minus 5, 0, 0, 0, 0, 0. This is also an eigenvector. These all have the same direction, and with vectors we only care, well, at least with eigenvectors, we only care about its direction. We don't care so much about its magnitude. It can have any magnitude. And so if I plot this on a graph, so we plot our 2 lines, we get something that looks like that and something that looks like that. So this is our y is equal to minus x, and this is our y equal to, is it 2/3 or something? I think it's 2/3. And so if you like, you give me a vector, say a vector that lies on, I should do that line, it's easier. Say a vector like that, so 1 and 2/3. And when you apply your matrix A, so if you're like, this is our x, then once you apply your matrix A, the thing that you'll get will be on the exact same, be on the same line. And in this case, because our lambda is equal to 10 for that one, the vector you'll get out will be 10 times bigger than the original vector that you got. So 10, 1, 2/3. Cool. Does that make sense to everyone? Cool. Yeah, it's saved. Cool. Okay, so that's the kind of gist of eigenvectors. But now I'm going to go into like how you can. So one of the applications of eigenvectors is if you get a weird matrix given some fancy ass matrix and you don't know what it does, you can calculate its eigenvectors, and from its eigenvectors and values, you can kind of figure out what the matrix actually does. So if I give the example of Okay, so there's three main examples that I'm going to cover today. There is another one, but let's not get into that. So the main ones are reflection, rotation, and scaling. So if I take a random reflection matrix, 0, 1, 1, 0, was it? 1, 0. And I work out its eigenvectors and values. We get lambda equal to 0 and minus 1 in my head. So our vectors will be, I think, 1, 1, lambda equal to minus 1, minus 1, 1. Okay, so one thing to note with the reflection, I'm going to tell you right now, this is a reflection matrix. And one thing to note about the reflection matrix is you'll always get two eigenvectors. So you always get two eigenvalues, and one of your eigenvalues will always be equal to 0, and one of them will always be equal to a negative number. I can explain that geometrically, and also in one of the problems you have to try and prove it for a general case as well. But that's, so if you ever see two eigenvalues and one of them 0 and one of them is negative, you know straight away that your matrix is most likely a reflection matrix. And so the way I'm going to try and prove to you, show this to you, is so what do the lines look like? Y is equal to x. So that's the 0 line, so our reflection line. So if you like, for this matrix, that's the reflection line. So you put in some vector, say like this, and you'll get out some vector like that. Or you put in some vector like, what's a weird one I can do? Like that, and then you get something like that. So it just reflects along the line, that's all it does. And using this relation and using our two eigenvalues, we see that one of our eigenvalues is equal to 0. Now, what the 1 equal to 0 means is the vector that lies, how do I say that? This vector essentially is the line of reflection. For the eigenvalue of 0, the vector that you get out will be parallel to your reflection line. And the reason why this is because if you put in some vector, in this case 1, 1, into your matrix and you times it by AX, if you just do it geometrically actually, and you just say, what is the reflection of that, you'll always get the exact same vector. Actually, sorry, no, not the exact same vector. You always get 0. Yeah, so if you ever put any vector, say like this one, so I think this is like minus 5, minus 5, you reflect it, ignore the matrices, it just reflect it on that line, you'll always get that equal to, any vector along that line equal to 0, because there's nothing to reflect. That makes sense. And the other eigenvector comes from the what do you call it, the vector that's perpendicular to your reflection line. So if you like that one. And so whatever vector you put along here, when you reflect it, you'll just get the opposite vector, one that points in the other direction. And so that's where our negative sign comes from, because if you like, this is x, and this is ax, and ax is equal to lambda x, and because our lambda is a negative number, we're just going to get the exact same vector, but in the opposite direction.
Just a question, are you sure that it's 0?
Which one?
Eigenvalue for the first one, I think.
This one.
Yeah, that's supposed to be 1.
Let me check. So you get lambda squared minus 1 equal to 0, so lambda squared equal to 1. Oh, right, yeah, it's 1.
0 is the trivial case, almost every effect that is in matrices is.
It might be 1, yeah. But then how? We should get 2, though.
Yeah, you do get 2.
You do get 2. Oh, yeah, plus minus 1. Okay, I'm being silly. Oh, yeah, so any vector that you put along that's a parallel to your reflection line, you'll just get the exact same vector out. That's what I found. It's not 0. Okay, so that's the reflection case. So note that you'll get a positive eigenvalue and a negative eigenvalue, and you know its reflection, and you know the positive one is going to be parallel to your line of reflection. At least that's reflection. Now we consider scaling. 5, 0, 0, 5. Does anyone know what this matrix does? Sorry? Yeah.
Aha, I see it.
Because if you had some...
50. I was like 50.
50. So if you what you'll get out will just be 5 times by x and 5 times by y. And so actually the eigenvectors of this is quite trivial. You know that your lambda will equal to, I think, 5. You'll only get one solution of 5. You should get plus minus 5, shouldn't you? Yeah, let's ignore that one. So you get a lambda of 5, and so if I show this to you on a graph, that's your x, that's your y. If you put in some vector like that, if this is your x, what you'll get out is just some vector that's a little bit bigger than the original vector. Niraj, do you only get one solution for this?
Sorry?
Do you only get one solution for this one?
You get two, but one is trivial, so yeah, one.
Oh, okay, yeah. So with scaling, you'll only ever get one solution, and you know that the vector will be like, how do I put it? It's like the direction of the scaling. You could scale it in that way, you could scale it in that way. In this case, it's scaling the x and it's scaling the y by the same amount, by 5 in this case. And so that's scaling.
If that's your question, give the eigenvector, what would the eigenvector be?
That one will just be x, so 1, 1. So if you like this line here is y is equal to x, and so your eigenvector will just be 1, 1. If you like, that's the direction of scaling.
That's the direction of scaling.
Yeah.
So vectors in that direction are actually scaled.
Yeah.
They are not returned back. But anything in the perpendicular direction is given.
Say again.
Anything in that direction would not be scaled, so it would just return itself.
Oh, yeah.
So try that, put in negative signs on the y and see what happens.
Where?
Oh. Yeah, I mean, try putting, say, 1 minus 1 in that. 5, 0, 0, 5. 1 minus 1.
0.
5.
Oh, 5.
Minus 5. Yeah, so 5 times 1 minus 5. You get the same vector.
Okay, yeah.
Why is it scaled? It shouldn't be scaled. This is identity vector. This is 5 times I. This is bad vector. Very bad vector.
Say where?
Yeah, it's a bad vector. It's 5 times I.
Oh, right,
It just
okay.
returns anything that's there over here.
Okay.
Think about it.
Yeah, I get what you mean.
Yeah,
So with the identity case, you get 2 eigenvectors. Sorry?
2 eigenvectors, literally any vector.
Yeah.
It's an identity.
That was to trick you. Do you know any scaling ones? Give me a scaling one.
3001.
3001. So
use just an x scaling.
So yeah, that one. I'm sure I'll do it. So this one's going to scale on the x-axis by 3.
No, it scales both in x and y.
Really?
No.
No, it's just x.
So that's just x.
You'll get 3 and you'll get what? 3x
Oh,
and
1.
y.
Okay,
Yeah.
One
Okay.
is a tricky one. Okay, good.
1 is a tricky one.
1 is a number, but it does nothing.
Yeah. 1 minus lambda equal to 0, so lambda is equal to 1 and 3. And what do the vectors correspond to? So
Teach them to find the vectors as well.
yeah, it's in the problems.
You should teach them.
Okay, so your eigenvectors will be along your x-axis and I think perpendicular. No, 3. I think 1 perpendicular, because if you have a scaling that goes in that direction, the y isn't really affected, and so your y, if you have like a y component, a y vector, say in that case 0, 1, you put it through our matrix 3, 0, 0, 1, and you'll just get
0, 1.
0, 1. So the same vector. So that's where your 1 comes from. Cool. And last one, rotation. Oh, yeah?
I don't understand what you're doing here. Are you saying that this result here, this means that it doesn't scale? Or
So,
it does scale?
Does scale. Let's to show what it does, if I may, thank you. Let's just put some examples in, just some random vectors. 1, 2, let's see what happens over here. That is 3. That is 2. So the y isn't scaled, the x is scaled. So if you have some vector like that, which is the x component over there, let's say this is ax. A is a bad choice, so you should have told me. The answer is v. Vy. This guy is just kept as it is, but this guy is scaled twice. So once, twice, thrice, and the resulting vector would be that. So this guy, something like that, is scaled like that. As we can see, anything in that direction would just be scaled, literally just be scaled. Anything in that direction, though, would just be itself. And anything else, you'd have to calculate the x component and the y component, just scale the x, take the y, draw the vector. So, and the trick to that is when you have a matrix, you have, let's take a 2 by 2 matrix. The first term, 2 by 2 tells you that you're working in a 2-dimensional space. The first term is how the x changes with x. So how the final x is related to the initial x. This guy is how the final y is related to the initial x. I'm going to explain what I meant. And that's the initial final x related on the final initial y, and that's the final y related to initial y. So if you have zeros over here, it means that it's like x squared, rather x1, x2, x1, y2 plus x2, y1, and y1, y2. So these guys essentially just are like, if there's something over here, it just means that your x, for example, that guy just is scaling in that direction, that guy is scaling in that direction. That guy, these two guys, are more like, here the x depends on y, and here the y depends on x sort of situation. So what I mean is that if you have anything over here, it sort of means you're rotating stuff. But if you don't have anything there, and you have something over here, it just means you're scaling it rather. I mean, if you look at a few examples and put some vectors in, just play around. There should be some software online which does that. No? Okay.
Bring it up
There
now.
should be something online that does that. And when you just put examples in, you're going to see how it really depends.
Yeah.
There's this intrinsic sort of dependence that if you know, that's really, really good, because this is just 2 by 2. You probably are going to do n by n generalized case. That's more computational.
Can you scale something down?
Yeah. If you want to scale it down, I mean, in the opposite direction, just put a minus sign. If you want to shorten it, just take a fraction, say 1/2 or something like that.
0, 0, 1. So if you like, what this one's doing is whatever x, should write x, y. So if we take some general vector x, y, what it's doing to the x is it's dividing whatever x coordinates by 2, and it's scaling the y, just keeping the y the same. And then if you wanted like a negative one, say -1, 0, 0, 1. X, y. This is just making the whatever x you had originally, it's just translating it, so from here to like that way, making the x negative. So for example, if you put in an x of 1, 0, what you'll get out is just the negative 1, 0. And so it's rotating it like sort of doing like that. Cool. Hopefully we'll go over some problems, and then you'll probably try and make a bit more sense when I go through all of them.
Yeah, I mean,
What is the eigenvector of the negative translation, wouldn't it be an imaginary number?
Well,
There would be the first one,
yeah.
but then so you can imagine there might be a second one.
Oh, I mean, yeah, I mean, sure, you can have stuff. I mean, say you have something like plus over here, that might give you lambda to be, or rather not like that, rather something like that is plus 1 is equal to 0. This you don't use because you know that the determinant is 0, but if it isn't, you're going to end up with something like that, which would give you complex solutions, which would mean, yes, there would be an imaginary sort of vector. Now the problem is, this is real space, and what it tells you is that these sort of equations are not permitted over here. It also tells you, well, and one of the reasons why is probably you must know the motivation behind why we're using, determinant should be 0 sort of things. These are called observables, and what it means is that physical quantities like distance, position, momentum, energy, all of these quantities, which normally we use matrices to find out these quantities. I mean, yeah, you put that the matrix over here, the vector over here, you get the eigenvalue, should be the energy or something like that. Sorry. Those values are always real. So remember, you can't have a complex number over here for observables. And well, if you're mathematically inclined to do such stuff, inclined to do that stuff, you can do it, but it has no physical meaning because all those values should be real, can't be complex or imaginary essentially. Oh.
So if you are interested, there is actually an extra problem in the thing that will deal with imaginary vectors.
It's just that when you talk about imaginary things, you can't be physical, they're not real. You can't have imaginary distance. You can, but it wouldn't be real.
Cool. So any other questions before we start off?
Difficult ones, man. Like
These are difficult, man. Bruv. Took me a bad time.
Trust me.
Oh, wait, let me just change one thing. So that's supposed to be sort of power.
Right.
Oh, nah. Never code again. Get it.
LaTeX. So yeah, these are the problems. Some of them are easy, some of them are really hard. And luckily, I know all the solutions now.